So, yeah, I don't need to do that right now. Okay, so we're still in section 1.7. And so that means we're still doing the chain rule. And what I want to do to warm up today, oh, sorry, I just saw Zach chatted. Can you do an example relating to the FPS? So like which part of it, Zach? I'd be happy to, but is there some aspect of it that you're hoping I talk about? I mean, because, like one could say, well, like everything we've been doing is related to it, but okay, yeah. So let's talk about question 3 a little bit. So, like I said, I'm not going to do the question for you, but this is very similar to what we did on Monday when we talked about, I can't remember what the functions we used were. It was the cost, right? The cost of producing X items, and then X is the number of items produced, right? And the thing was, we had a formula for C. It was, some function of X, right? Like, I'm just going to make it up here. 5x squared plus 10. And X was a function of time. And it was like 2t plus 100. I'm just, making something up here. And so, if we wanted to find dc dt, right? How does cost depend on time? So t is time, let's say in days, right? So we have a relationship here, right? T feeds into X, and X feeds into the cost, right? So those relationships are given by those equations. What about the relationship between cost and time, right? There is a relationship, but it's not direct. So how do we figure out the nature of that relationship? Well, I mean, what it is, it's C composed with X of T. So one way to solve this problem is to just do the composition, right? Like cost is a function of X and X is a function of T. So if we just compose the two functions, it would look like that, right? Plug X into T, and I plug X into C. And I could just FOIL that out. And I would get 4t squared plus 400t plus that plus 10. So I'd get 20t squared plus 20 or 2000t plus 50,010. Right? So there's C composed with X. So it's C as a function of T, you might say. So if I wanted to find the derivative, I could just use that formula, right? Because the derivative of C composed with X of T, I mean, I have a formula right there, right? So I can just use it. It's 40T plus 2000. I use the power rule. So this actually relates to the first couple problems on the formative problem set, because I asked you to do it 2 ways, right? This is one way. You just find the composition formula and take the derivative, right? And so there it is. Now, we could have done it differently. We could have used the chain rule, because the chain rule says, if I know the derivative of C as a function of X, and I know the derivative of X as a function of T, then I just multiply those derivatives to get the derivative I want. Right? This is how we label this diagram here, right? So here's like the speed of X compared to T. Here's the speed of c compared to x. So those two derivatives, when you multiply them, you get the speed of c compared to t. And so what we can do is just calculate. We don't have to actually find a formula for the composition because dc dx is 10x, right, by the power rule, times 2, right? Because, again, power rule, or x is just a linear function, so derivative is 2. So we get 20x, and if we plug the formula in for x here, right, we want to end up with the t variable, then we get 2t plus 100. We get 40t plus 1,000. So notice, they're the same. Sorry, my phone. Yeah, sorry. Okay, so in other words, like, what am I trying to say here? Like, how am I answering your question, Zach? So to answer your question, it's the same thing that we're doing here. What we're doing in problem 3 is the same thing as we're doing here. We're just taking the pieces, finding the intermediate derivatives, right, the derivative of each piece, and multiplying them together using the chain rule to get the derivative we want, right? Because in that problem set, it's not c and x, it's p and n, right? And so, but it's the same kind of process. Is that addressing your question? Like, is that helping? So Yazan also has a question. I'll get to you in a minute, Yazan. Okay, Zach says, yeah, that's good. But let's go on to talk about question 4, because Rejoice is asking about that. Question 4 is about compound interest. Now, we're looking at it as a function of r, okay? So, you know, it's a function, right? And we're just taking the derivative. Right, so like, you know, we could write any function of r, right? It's like 10, you know, r minus 5, you know, to the 7th power or something, right? Whatever. It's not the same function, but it's a similar function, right? So how would I use the chain rule? I would, the 10's along for the ride, bring down the 7 by the power rule, right? That's like the outside function is the 7th power, times the derivative of what's inside. Since it's just r minus 5, it's just 1. The derivative of what's inside is just 1. We get 70 r minus 5 to the 6th, right? So that's I mean, if we wanted to call this function, you know, b, whatever, just get, then db dr is that, right? So dA dr, we want to find the derivative of a as a function of r. And then in b, you know, we're just going to take, you know, your formula should have like t and r in it, because t and r show up in your formula for a. So then I said, okay, well, what happens when you plug in these values? And what are the units? And then try some other values and plug in the units. The one thing you want to keep in mind here is that r, the way I've set it up, r should be like let's say that the interest rate was some crazy amount, like 30%. Like, that's not going to happen. Let's just say it was 30%. Then r should be 30, not 0.3, right? So notice r is not the decimal form in this problem. It's r percent, right? So r should be a percent, not a, like, if it was 90%, r would be 90. If it was 5%, r would be 5, right? You see what I'm saying? So you do want to pay attention to that. Is that relevant to what you're wondering about, Rejoice? Okay, good. So that brings us to Yazan. Like I said, this is a perfect day for questions. You're not cutting into my lesson plan, really. My lesson plan is flexible today. So, Yazan.
So I have a question, which is probably like the last question in the formative problem set. So it says use the chain rule, but there's only like one, like, variable, or like it's only X. There's like no other thing. So do we just like find like, how do we find it? Like just,
Yeah, good question. So this gets back to what we were talking about on Wednesday when we were like, how do we recognize the opportunity to use the chain rule? And so, let's look at a similar problem. Y equals like x squared plus 3x. Okay. What's the derivative? Well, I mean, it's true. There's no like third variable, right? And so how do we approach it? Well, what we could do if we want is actually create a third variable to represent sort of the inside part of this function, right? Because there are two layers to this function, you might say. There's the square root layer. Oops. Don't want to do that right now. There is sort of the square root layer, and then there's inside that, there's the x squared plus 3x layer. So we could call that inside part u, right? So u is going to be x squared plus 3x, and that means y is just the square root of u, which we could rewrite as u to the 1/2, which is probably a good idea since we're going to be using the power rule to take a derivative. So if we set it up that way, then dy dx is just dy du times du dx. And dy du is 1/2 u to the negative 1/2 by the power rule. Du dx is 2x plus 3. And so what we get, if we go back to the x variable, we get 1/2 x squared plus 3x to the negative 1/2 times 2x plus 3, which we could simplify a little bit to 2x plus 3 over 2 x squared plus 3x. Now, we don't have to do it that way. Just, we don't have to do it exactly like that. We could just sort of talk our way through it, right? So, I mean, if I want to take the derivative of x squared plus 3x, well, I still probably want to write it as a 1/2 power because that's just going to make it easier to think about. And I would say, okay, what's the derivative of the outside function? Well, the outside function is 1/2 power, so I just bring it down, subtract 1, times the derivative of the inside function, which is just, 2x plus 3. And I get the same thing, right?
okay, so it doesn't matter, like, to use specifically the chain rule. We could just go and solve it as a derivative, right?
Well, I mean, you are using the chain, whether or not you think about it that way. Like, either way I'm doing it here, I am using the chain rule. It's just I'm using more or less like detail, right?
Okay, okay.
Yeah. So now, if I say show your work, I mean, either of these would be acceptable work. Wrote in the red and the blue. Of course, for the problem in the formative problem set, it's not necessarily just the chain rule, is it? Because you have to either use like the quotient rule or the product rule along with it. So you want to show some of the steps. Like, don't just give me your final simplified answer, because if you do that, then I don't have any reason like to can't tell whether or not you just asked the internet to do it for you, because there are internet websites that can do that for you, right? So I want to actually see that you work through the steps to get the final answer. Okay, so these are all really good questions. Hopefully that helps clarify things. Let's actually, to build on this, what I was going to do actually, I'm going to build on this guy, this right here. And what I want to do is take that example. We figured out the derivative, right? It's equal to what I have up there, 2x plus 3 over 2 x squared plus 3x. So, let's do this. What is the tangent line? to y equals x squared plus 3x through the point um, 1, 2. So actually, let me make sure I'm doing that right. So notice if I plug in 1, I get 1 plus 3. Yeah, so that's right. Equals 2. Right? So 1 comma 2 is on the graph of that function. So can we find an equation for the tangent line through that point on the graph? Well, I'm just trying to connect with that, right? I'm going to try to reconnect with that question. We've done that a bunch. And on the last formative problem set, I think we had some stuff like that, and it didn't always go well. Just to be honest with you, like, you know, when I was grading it and similar problems like that, come on now, I don't want to do that. You know, it didn't always go well. It didn't always come together. So I want to make sure we're understanding this. How would I use the derivative to figure out the equation of the tangent line? Well, okay, well, let me say this. What do we need? To get the equation of a line, there's different ways to do it. We need a point, and we need slope. That's one way to do it, right? I'm going to pick that because, look, we already have a point. Right? We already have it. I gave it to you. And the slope, well, let's remind ourselves. The slope is given by the derivative, right? That's what the derivative is. It gives you the slope of the tangent line at a given point. And so it's equal to our derivative at, Izan is asking about this in the chat, but we actually don't care about the point 2. That's the y, right? We don't care about the y coordinate here. We plug in the x coordinate, right? At that x value, the dy dx gives us a formula for the slope through the graph at that x value. And so in this particular case, when I plug in 1, I get 2 plus 3 over 2 square root of 4. Right, I'm just plugging the equation. And so I get 5 over 2 times 2, which is 5 over 4. So I've got a point and I've got a slope. We should be able to do this, right? We just use the point slope form now. So I take y minus 2 equals 5 over 4, x minus 1. I get y equals 2 times, let me clarify that a little bit. 5 over 4x minus 5 over 4 plus 2. So y is equal to 5 over 4x plus 3 over 4.
Quick question.
Sure.
Where did the top of the fraction for, I think it was like 2 plus 3 come from?
Yeah, so if I go back up here, I'm plugging in to the derivative, right? dy dx. I'm plugging in x equals 1. And so I get 2 times 1 plus 3.
Okay, thank you.
Yeah, sure. And so, yeah, good question. I mean, if there's ever a detail that's not coming together, just ask about it. And so that's our proposed tangent line through that point on the graph. And the nice thing about it is we can check it and see if it actually looks right. Because we can go to Desmos. Actually, wait, let me write it down before I leave. So if I go to Desmos, some other stuff here, and we graph our original function, notice it's got 2 pieces. We're not going to care about the one on the left. We're only caring about the one over here to the right. And so we're saying that, actually, let me set this up a little differently. Let's call this f of x. Right, I'm going to give it a name. And then let's say that, yeah, well, let me just do it this way first. I'll just put in the equation for our tangent line and see what it looks like. 5 over 4 x plus 3 over 4. And look, let's put in that point 1, comma 2. Here it is. So in terms of appearance, does it look right? Okay, so there's the point that we're interested in. Does our tangent line seem to be correct? Well, it sure looks like it, right? I mean, I'm just trying to connect back with these ideas that we've been developing all along.
Quick
Right, they
question.
haven't changed. Yeah, go ahead.
When you plugged it into Desmos, you plugged radical x squared over 3x or something. Wasn't there like a top, like a numerator portion to that, or?
That's the derivative. So notice I'm not plugging in the formula for the derivative here. That's a good thing to point out, because all I've graphed is the original function, and then I graphed the tangent line equation that we obtained.
Oh,
So-
all right. I was thinking the numerator and stuff was in the original function. My bad.
Yeah. Yeah. So yeah, it wasn't. Yeah. But good question. Good thing to clarify. Right. So it does look like it works. And remember, what do we mean by looks like it works? Well, what we mean is when we zoom in on that point on the graph, it looks like the graph becomes the tangent line, right? That's what a tangent line should do. It's meant to approximate the graph near a single point. That's why we use the slope of the tangent line to describe how the graph is changing at that point. Okay? And look, I can show you something here. Let me actually delete that. We don't care. We don't have to focus on just that particular point. Let me say why. Sorry. Let me see if this works. Let's call it m of x equals. Let's see if Desmos can handle this. F prime of x. Okay. Okay, it works. It can do that. So here's what we're going to do. So I just called m of x equal to the derivative at the value a. So if I write down a point slope equation for a line, for the tangent line, let's see what it looks like. So I'm going to do y minus f of a equals m of x, that's my slope, right? That's the derivative, times x minus a, right? That's the point form for the tangent line through the point a, f of a. Oops, and that should be a, not x. Let's see if this does anything helpful here. So look what it does. I don't need to draw that. So let's only focus on positive a values. Look what happens as I move that slider. Here, let me highlight the point a, f of a. Sorry for. So there's the point, right? Let's call it point P. So as I move my point, look at that. That if I set up my equation like that, where my slope of the tangent line is always equal to the derivative at a, I always have the equation for the tangent line. You see it happening. Sorry, it's probably a little choppy on your video because the live stream isn't super fast, but you can sort of move it around, and that tangent line always tracks the graph of the function. Okay. So there's nothing special about the point 1 comma 2. That's all I'm trying to show you. The same formula for the derivative can be used to find the slope of the tangent line through any point on the graph. All right, so any questions about that before we move on? I just wanted to build on that example a little bit, visualize the tangent line, reconnect with those ideas.
So I have a question.
Sure.
So what if we'll just say like the original formula, like f of x was for like velocity, right?
Mm-hmm.
So what would be the units for like the derivative or like the tangent line, kind of?
Yeah, good. Units are an important concept for us since we're doing applied calculus. Wait a minute. Oh, here we go. Let's talk units for a minute, because there's several questions on the formative problem set that ask you to provide units. So, if we have some function, f of x, let's say it's equal to, like you said, why not? Let's just say the velocity at time x, where x is in seconds, right? And let's say the velocity is measured in feet per second, right? Because you got to have units for velocity, right? So the units for x are, feet per second. Right? So I'm just making this up, but we'll start there. So then what would be the derivative units, right? What would be the units for f prime? Well, remember, it's always a rate. It's always a rate. Now, in this particular case, our original function already had units that were a rate. So what's the deal? Well, in this case, it's still just output over input, right? The rate is always given by that, right? If you're taking a derivative, the units are always going to be the output of f over the input of f. It's just always how it is. Because think about it. What is a derivative? It's the limit of a difference quotient, right? So the difference quotient is the change in f over the change in, like the change in output over the change in input. So the units for the difference quotient are output units over input units. So that's where the derivative units come from. And so in this case, it's going to be feet per second divided by a second. Or what you would often do is write that as feet per second squared, because you're dividing by seconds twice. So if this was velocity, so the velocity units, would be feet per second. Well, the derivative velocity, if we're talking about physics, we're talking about acceleration. And the units for acceleration would be something like this, feet per second squared, or meters per second squared, or whatever, measurement you're using over, or it could be miles per hour squared, right? That would be the acceleration of your car. If you're driving at whatever miles an hour, the acceleration would be miles per hour squared. So like hour squared, miles divided by hour squared. So does that address your question, Yazan? It looks like it based on your chat. So there's a lot of stuff going on here, right? We don't want to lose sight of the concepts. So these are great questions. We have the chain rule. It kind of gives us a template, but how do we interpret the results? How do we understand the meaning and the use of what we're getting? That's really important stuff. So, all right. So I have an idea. And my idea is to let you guys talk through number 2 on the practice activity for this week. It's actually similar to some of the stuff on the formative problem set. And so, help. We have 21 minutes left in class. So if we take, 8 minutes, let's say, to let you guys talk through this problem, that'll give us some time to talk through it together. And I think it's very relevant practice. So, I can't tell if, nobody's told me, maybe a couple, maybe one or two. like I don't have a real feel for whether you guys love or hate or don't really care about the group work that we do with the breakout sessions, but so feel free to give me feedback if you have it. I think it's generally a good thing. So let me, well, actually, so what you probably want to do is open up the practice activity from the learning module. If you don't have that available, let's see here. I can share it here. But while I'm looking for this and sharing it, you might want to try to find it for yourself so that you have it in front of you. So let me open this in my app here. So the problem I'm talking about is right here. And so it might be too much to copy down by hand, but maybe you can, like I said, open it up on your own computer or your phone or whatever you're using so that you have it to look at. And we can try to talk about it together. So before I break you guys up into groups, anybody like not able to do this, like anybody not have access to the practice problem set?
Is this week 6?
This is week 6, yeah. So if anybody doesn't have access, let me know and I won't put you in a group. We can do it. You can be in my group, so to speak. But I prefer that you have your own groups. But if it's not possible, then let me know. Okay, so we're going to do 8 minutes for this. And I want you to just talk it out, see if you can come up with an answer. If 8 minutes is too long, you can just come back to the main group and we'll start talking about it. But, to actually give you time to hash it out a little bit. And since this is relevant to the formative problem set, feel free to engage. All right, so I'm going to start this and we'll come back I'll see you back here at 9:50, 8 minutes from now. Okay, see you soon. So we're back. I hope you made some progress on that. I was just talking to one of the groups because you can ask for help and I can come into your group and talk about it with you. So I was just doing that with one of the groups. And so maybe the best thing to do is just to work through it together real quick here. But did anybody have a question they wanted to ask before I start? Did anything like trip you up, or were you just not really sure what to do? Well, then let's just give it a shot together. But real quick, though, I know we don't have a lot of time, but we'll have enough time to finish this. Did anyone have trouble engaging with their group? Like, was anybody sort of like, hello, everybody, anybody there? Like, were you just kind of on your own, or did it actually work out somewhat? Because, you know, I wasn't in your groups, so I don't know how much interaction you had. So anyway, yeah. Well, I hope you were able to actually connect with your classmates a little bit. At least we had the opportunity on it, right? So D, if we plug in A and X, right, it becomes, so 0.85 times 5 is 4.25, C plus 25, and then C is 140 minus 45, right? So 95 times W over 72 times 0.6, 43.2. So 95 divided by 43.2 is some ugly number. We can just, let's just round it, 2.199. Okay. Then dC, so now D is a function of C. If we expand that out a little bit, it's just this, right? So we get 4.25. And what are the units? Well, C, it's this creatine clearance thing, right? So the input is the creatine clearance, output is milligrams. So it's milligrams per creatine, just put creatine. dCdW, 2.199. So these are both linear functions. And the output for this is creatine units over creatine clearance units over the input is W, and W is weight, so kilograms. Okay, so then what do you do with these pieces? The chain rule says that dW, so the derivative of D dosage as a function of weight, is the product of these two intermediate derivatives, which we now know is 4.25 times 2.199, which is 9.34, let's say 6. We'll round it to 3 decimals. And what are the units? Well, the DD/DC units were milligrams per creatine unit, creatine clearance, whatever's. And then the other one was creatine clearance unit per per kilogram. So the creatine units sort of cancel, if you want to say it that way, and it's milligram per kilogram. So milligram medicine per kilogram of weight. So that would be your final answer. So don't overthink it, right? I mean, we're using the chain rule, right? So what might be confusing here? Well, one thing that might be confusing is all the variables, right? And this Leibniz notation. Like, what are all these things? Well, try to just read that for what it says. It's actually a helpful way to do it, I think, because it tells you, like, okay, the numerator is the function, the denominator is the variable. So capital D is a function of C, so we take dC for the derivative. C is a function of W, so we take dCdW to get the derivative, right? And we can also think of D as a function of W, right? Because it does depend on weight indirectly. So dD/dW is the derivative of dosage as a function of weight. So is this helping? I mean, is this clear or not? Anything about it that you want me to talk about some more? Rejoice, you were asking me about it. Is this helpful now that we're looking at it?
Yeah.
Okay. I mean, sometimes it's hard to know what to ask. So, I mean, it's fine just to let me know, like, I'm still not getting it. Like, even if that's all you can say, that helps me to understand where you're at, how you're doing. So Shane says it helped. That's good. It's good feedback. So, we're trying to just get a feel for what the chain rule is actually good for, not just what the template looks like. All right. Well, so to finish today, actually, wait, we might as well just stay here. Because to finish, I mean, sometimes we do want to just be able to get the template to work out, right? So Nathan says, still not totally getting it, but it helped. Okay, that's progress. I mean, so let me just try to make sure that it's coming together here, though. I mean, what are we doing here? What we're doing here is still just using I'll just squeeze it in up here. We're using the Leibniz version of the chain rule, right? And why does this make sense? Like, I really do think this wheel diagram can help us realize why it makes sense to do it this way. Well, sorry for all the scrolling, but like, what we're doing here is we're saying, okay, I have kind of 2 steps in this process, right? So I can start with weight, and that takes me to my creatine clearance, right? Because I have a formula for weight in terms of creatine. Or sorry, yeah, that's right. Weight takes me to creatine, and then I can plug in creatine and get my dosage, right? So I have these 2 steps. And And so what I want to try to figure out is, what's going on with like the whole thing. If I put those two steps together and go from weight straight to dosage, how is that behaving, right? And so the chain rule says, if you know what happens along the way, if you know how D depends on C and you know how C depends on W, then you just multiply them, and then you know how D depends on W. Right? That's what the chain rule is telling us. And so on a practical level, what we've got to do is just find those intermediate derivatives, right? So first we got formulas for them in part A, then we found their derivatives in part B, and then we said, okay, the chain rule says to multiply them in part C, and that gives us the derivative we wanted. So I'm just trying to pick up on what Nathan is saying, because there's two aspects to it, right? There's the concept, there's the why, and then there's the how. And I think probably the how is easier to fix, right? If we're not sure about the how, well, I mean, there's plenty of practice here. Like these have answer key. There's an answer key for this in the module, right? So you can look at the formulas for these derivatives. So the how, I think, is probably easier to fix if you're not sure about that. But the why, that's what I'm trying to talk to you about here, because that might be a little harder to determine without guidance. So, take it or leave it, but I'm just trying to offer some additional thoughts about that. So we are about out of time. I will let you go here in a second. So if you're still struggling with the chain rule, I encourage you to look at the practice activity answer key for one. Look at the PowerPoint slides in the learning module. Look at some of the videos and stuff on MyMathLab. Look at the study plan questions and do some practice problems that won't hurt your grade, right? Even if you get them wrong. Do the MyMathLab problem set, which is for a grade. And, if you do all that, that should help you, beef up on your skills, and you can do the formative problem set if you haven't already. So, it takes effort, but, and this is a more difficult concept. That's why we spent all week on it. Hopefully we can figure it out and forward from here. So Yazan, real quick, before I let you go, is there any extra credit in the future? I don't do big extra credit point stuff, really. Instead, so, a lot of times that's meant to provide like a cushion, like, okay, people lost points here and there, they can make it up with some extra credit. Instead of doing that, I drop a lot of low stuff, right? So the cushion I provide is in dropping your lowest 2 formative problem sets, your lowest 2 MyMathLab problem sets, your lowest summative problem set, and your lowest 2 communication requirements. So that's actually, I would say, a fair amount of cushion right there. And so, yeah, that's how I do it instead of some extra credit, because, that's just my philosophy on it. So it's not the only right philosophy, but that's the one I embrace. So anyway, I'll let you go, and hopefully I'll see you all back on Monday. Hope you had a good weekend, get everything finished, and so take care.
I have a quick question.
Sure.
So with the B, how will you do it without having like the 4 power and like the 8 power?
Yeah, so you're going to need the product rule and the chain rule for that one, right? Because you've got 2 functions multiplied together, right? You've got like this piece times the other piece. Right? So like you can think of this as F and G, right? And then so you use the product rule and the chain rule.
Oh, okay. So you're gonna do the product rule first, then you do the chain rule after?
Sort of, yeah. Yeah, that's one way to think about it, because it's going to be F prime times G plus G prime times F. And so to get F prime and G prime, you're going to use the chain rule, right? So yeah, like the first thing you do is set it up using the product rule, and then to get the pieces, you have to use the chain rule. Yep.
Oh, okay.
Okay. All right. Well, you can always reach out via email if you have other questions. Otherwise, I'll see you Monday.
Okay, see ya.
Mm-hmm.